It is a common engineering assumption that every computation must consume a fixed minimum amount of energy. The equation E greater than or equal to kT ln2 is often cited as a universal limit on every bit operation. It is not. Modern processors generate immense heat. A standard CMOS logic gate emits thermal energy as it charges capacitances and fights leakage currents. But in an idealized abstract logic gate, completely insulated from engineering inefficiencies, calculations can operate with exactly zero heat dissipation. Consider a logically reversible operation, like a NOT gate. Because the output uniquely determines the input, a 0 becomes a 1, and a 1 becomes a 0. The system retains the history of its states. In principle, you can execute this operation with arbitrarily small energy dissipation. The Landauer bound does not apply indiscriminately to all digital activity. The thermodynamic debt only comes due when distinguishable alternatives are merged and the physical records separating them are destroyed. The absolute minimum energy cost of computation arises exclusively from logical irreversibility. Specifically, taking an initially unbiased binary memory, where a 1 or a 0 are equally likely, and forcing it into a known, definite state. The connection between information and thermodynamics begins in 1871. James Clerk Maxwell proposed a hypothetical entity, later called Maxwell's demon, capable of observing the speed of individual molecules. By sorting fast and slow molecules, the demon seemed able to decrease entropy and extract work, bypassing the second law of thermodynamics. Decades later, Leo Szilard translated this thought experiment into an analyzable engine. Szilard demonstrated that acquiring a single binary decision, knowing which side of a box a molecule is on, requires a compensating increase in thermodynamic entropy. In 1948, Claude Shannon established the mathematical foundation of this uncertainty. Shannon defined the bit purely as a measure of statistical probability. His theory deliberately ignored the physical wires, relays, and hardware used to transmit messages. Rolf Landauer closed the loop in 1961. He argued that Shannon's abstract information must be instantiated in physical matter. Because computing devices rely on actual physical states, any manipulation of that information is subject to the strict laws of statistical mechanics. What we now call a Landauer bit unites Boolean logic, Shannon entropy, and statistical mechanics into a single rigorous framework. It provides the exact mathematical weight of discarded data. To see how erasure generates heat, we map out a logical phase space. When a computer performs a logically reversible one-to-one mapping, distinct regions of this space simply swap positions. The total volume of accessible computational states remains constant. The physical mechanics change completely during a many-to-one operation, such as an AND gate or a reset command. If a system executes a reset, state 0 maps to 0, and state 1 also maps to 0. The system forgets its prior value. In the phase space, the two distinct logical regions compress and merge into one, cutting the volume of the computational subsystem exactly in half. Microscopic physical laws dictate that dynamics are strictly one-to-one. That phase space volume cannot vanish. The missing half is forced out of the computational subsystem and disperses into uncontrolled, chaotic environmental degrees of freedom. That dispersal of phase space volume into the surrounding environment is the exact mechanism of thermodynamic heat dissipation during computation. Heat dissipation is not the annihilation of an abstract symbol. It is the dispersal of distinguishing information into microscopic environmental records that the computer can no longer access. This chart shows the standard physical model for a single bit, a single particle resting in a symmetric double well potential. The left well represents state 0, and the right well represents state 1. Before we interact with it, the memory must be strictly unbiased. The particle has a 50-50 probability of occupying either well. The system contains exactly one Shannon bit of uncertainty. To erase this bit quasi-statically, the first step is to slowly lower the central barrier. This allows the probability distribution of the particle to mix evenly across the entire basin. Next, an external force tilts the potential to bias the particle entirely into the 0 state. The barrier is then raised back up, locking the particle in place, and the well levels out. When performed infinitely slowly against a room temperature heat bath at 300 Kelvin, this specific protocol exports exactly 2.87 zeptajoules of heat. That is the physical floor defined by the Landauer bound. This specific numerical limit assumes highly ideal conditions. If the bit is already known, or if the hardware allows a slight margin of error in the reset, the required entropy reduction drops, and the minimum heat limit drops with it. Theoretical models assume an idealized thermal bath, but actual processors operate within the microscopic, entangled, and highly chaotic reality of physical matter. Modern information thermodynamics replaces the classic inequality with a precise equality governing bipartite quantum states. This maps the logic system directly against its reservoir. The core of the math stays the same. The exact heat delivered to the reservoir is fundamentally driven by the decrease in the system's von Neumann entropy. But real physical interactions leave traces. We add a mutual information term to account for the thermodynamic cost of residual correlations, or entanglement, created between the system and the reservoir. Then we add a relative entropy term. This accounts for the free energy penalty incurred when a finite reservoir is displaced away from its initial state of thermal equilibrium. The famous KT-Ln2 bound is an asymptotic corner case. It only appears when these complex reservoir correlations and displacements are perfectly zero. Saturating that limit requires a quasi-static protocol that takes an infinite amount of time to complete. Real computers have deadlines. When evaluating finite time erasure, the formula expands. Operating at any real-world speed introduces an unavoidable macroscopic excess heat penalty. This excess heat is inversely proportional to the duration of the erasure protocol. The faster a gate forces a bit to reset, the higher the thermodynamic toll. Physicists map this high-speed penalty as an optimal transport problem. The protocol's trajectory acts as a path across a curved statistical manifold, generating thermodynamic friction as it moves. To minimize the excess work caused by this control velocity, optimal computing protocols must locate the most efficient paths, the geodesics, along this metric. Computational speed acts as fundamental thermodynamic friction. It transforms a static limit on entropy into a dynamic geometric optimization problem. When we step back from isolated single bits to look at the macroscopic, interconnected reality of modern circuit architectures, the constraints shift. In quantum computing architectures, the core gate evolution is unitary. The logic operations are inherently reversible, meaning the central calculations do not produce the primary heat. Instead, the Landauer thermodynamic debt migrates to the surrounding infrastructure. The exact physical toll is paid during state preparation, the measurement of error correction records, and the resetting of ancilla qubits for reuse. Circuit architecture also introduces the thermodynamics of modularity. Breaking a computer into isolated components generates excess entropy because separate gates routinely discard systemic correlations that a globally optimized machine could preserve. Evaluating the true thermodynamic efficiency of a computer requires analyzing the full error management cycle and memory hierarchy. You cannot determine the energy cost simply by multiplying the number of logic gates by a theoretical constant. The Landauer bit is not a specific type of logic gate, and information is not a physical substance possessing a fixed energetic weight. It is the canonical measurement of exactly one bit of entropy reduction being exported from a logical system into the surrounding physical degrees of freedom. Its value does not lie in estimating the power bill of a data center. It provides an absolute benchmark for separating fundamental thermodynamic constraints from the temporary inefficiencies of processor architecture and switching speed. It stands as the exact mathematical bridge connecting the abstract rules of logical inference with the unavoidable reality of physical entropy reduction.